In the last lecture we had derived the mass conservation equation in a Cartesian coordinate system. If you recall, we had taken a coordinate system where the three coordinates are the x, y and z coordinate in a 3-dimensional space with unit vectors in the 3 directions. Okay. This is Ey, this is Ex, this is Ez. Okay. And we had done this balance over this differential volume for the change in concentration over a time delta t. Okay. The change in concentration is because of mass coming in and mass going out along the surfaces bounding this volume, 6 surfaces, 2 perpendicular to the x direction in the front and back, 2 perpendicular to the y direction left and right, and 2 perpendicular to the z direction bottom and top. And we had looked at the mass in and mass out of each of these surfaces due to the flux. Flux of 2 types, one is due to the fluid flow due to the velocity field and the other is due to the diffusion flux. So, we had written an expression for the change in mass in time delta t and divided throughout by volume, divided throughout by time to get a differential equation. Okay. And if you recall, that differential equation that we had got was of the form partial c by partial t plus partial by partial x of c Vx plus partial by partial y of c Vy plus partial by partial z of c Vz is equal to minus partial jx by partial x minus partial jy by partial y minus partial jz by partial z plus the rate of production of mass. Okay. Now, we have defined it in vector notation. The velocity vector is defined as Vx Ex plus Vy Ey plus Vz Ez. The flux vector, note that the velocity has both magnitude and direction in 3-dimensional space. Similarly, the flux has both magnitude and direction in 3-dimensional space. So, this is Jx Ex plus Jy Ey plus Jz Ez, and we had defined a vector operator. The gradient operator is equal to Ex partial by partial x plus Ey partial by partial y plus Ez d by dz. Using these operators, for example, if I take the dot product of Vc, okay, the dot product of the gradient operator with the velocity times the concentration. Okay. So, the dot product of 2 vectors should be a scalar. This is equal to Ex d by dx plus Ey d by dy plus Ez d by dz. Okay. Dotted with C Vx Ex plus C Vy Ey plus C Vz Ez. Okay. Dot product of Ex dot Ex is 1, Ex dot Ey is 0, Ex dot Ez is 0 and so on. Okay. So, if you just take the dot product, also note that Ex, Ey and Ez are independent of x, y and z. They are the same at all positions in space. Okay. Therefore, when the derivative acts on Ex, Ey and Ez, you basically get 0. So, if you just take this dot product, what you will get is partial of C Vx by partial x plus partial of C Vy which is exactly what I had on the left side over here. Okay. Okay, so I can write it compactly in this form. Okay. Okay. Similarly, divergence of j, okay, del dot is called the divergence of j vector, is equal to Ex partial by partial x plus Ey d by dy plus Ez d by dz dotted with Jx Ex plus Jy Ey plus Jz Ez. Okay. Once again, Ex dot Ex is 1, Ex dot Ey is 0, Ex dot Ez is 0. So, you will get partial Jx by partial x plus partial Jy by partial y plus partial Jz by partial z, okay, which is exactly the negative of what we had in here. Okay. Which is exactly the negative of what we had in here. Okay. Therefore, this can be written, we can write the equation as partial c by partial t plus del dot Vc is equal to minus the divergence of j plus any source. Okay, that is a compact form of writing this differential equation. Del dot is called the divergence operator. Okay. Now, we know the constitutive relation for the flux. Okay. Jx is equal to minus d partial c by partial x okay. In the x direction, it is related to the gradient of the to the derivative of the concentration in the x direction, where d is the diffusion coefficient. Similarly, Jy is equal to minus d partial c by partial y, and Jz is equal to minus d partial c by partial z. Once again, I can write this in compact form, because I know that j vector is equal to Jx times Ex, where Ex is the unit vector in the x direction, plus Jy Ey plus Jz Ez, okay, is equal to Ex, I can take the common factor of d outside, okay, minus d into Ex partial c by partial x plus Ey partial c by partial y plus Ez partial c by partial z. Okay. Note that these Ex d by dx, Ey d by dy and Ez d by dz are just the operator that I had over here, the gradient operator. Okay. So, I can as well write this as is equal to minus d times grad of c, where grad of c is Ex dc by dx plus Ey dc by dy plus Ez dc by dz. Okay. So, that is the definition of grad c. Okay. So, I can substitute this expression for the flux vector into the mass conservation equation and get partial c by partial t plus del dot Vc, okay, is equal to del dot of the flux vector d grad c. Okay. Note that there are two negative signs here, one here and the other one over here. So, the two multiply to give you a positive sign, plus s. So, that is the mass conservation equation expressed in vector form. Okay. If the diffusion coefficient is a constant, if d is a constant, I can take it out of this derivative. Okay, I can take it out of this derivative, and the conservation equation will become partial c by partial t plus divergence of Vc is equal to d del dot del okay, C, okay, plus S. Okay. Now, that del dot del is equal to Ex d by dx plus dotted with Ex Ex dot Ex is 1, Ex dot Ey is 0, and so on. So, this just gives you partial square by partial x square plus partial square by partial y square plus partial square by partial z square. Okay. This is typically written as del square, okay, del dot del. Okay. So, therefore, the conservation equations partial C by partial t plus the divergence of V times C is equal to d del square C plus S. Okay, so, in writing these expressions in terms of vector notation, note that we have used 3 operators. Okay. The first one is in the Fick's law. Okay. This acting on a scalar. Okay. This derivative, vector derivative Ex d by dx plus Ey d by dy plus Ez d by dz acting on a scalar gives you a vector. Okay. So, the flux is a vector. Okay. This is called the gradient. This is called the gradient. Okay. When it acts on a scalar, the gradient of a scalar. Okay. This thing is the dot product of that operator and a vector. The dot product of the operator and the vector gives you a scalar. Okay. And this is called the divergence. Okay. This is called the divergence of the vector. Del dot any vector is the divergence of that vector. Okay. And then we have this operator. Okay. It is called the Laplacian, okay, acting on a scalar. Okay. So, these 3 vector operators are what we have used over here. So, I said this is the form of the conservation equation, okay, in vector notation, okay, and we had also written the form of the conservation equation in terms of components over here. Okay. So, you can see that this form of the conservation equation is written in terms of components. Okay. This in terms of components is specific to a Cartesian coordinate system. Okay. Okay. It is specific to a Cartesian coordinate system because we have the components in terms of Cartesian coordinates. Whereas this form here is general. Okay. It is applicable in any coordinate system provided you derive the operators here, the gradient, divergence and the Laplacian for that particular coordinate system. Okay. Okay. So, this vector form of the conservation equation is a general result, whereas when you express it in different coordinate systems you will have different expressions specific to that particular coordinate system. So, with this introduction let us go on to the next part, which is basically a spherical coordinate system. So, a Cartesian coordinate system is useful if you are solving, for example, mass transfer or heat conduction in a rectangular geometry. If, for example, you want to solve the problem of heat conduction or diffusion around a spherical particle, okay, around a spherical particle of some radius r, say, okay. A Cartesian coordinate system is not convenient here because the surface of the in the Cartesian coordinate system is x square plus y square plus z square is equal to r square. Okay, so, that defines the surface and you have to apply conditions on that surface. It is more convenient to solve this in what is called a spherical coordinate system, where one of the coordinates is the distance from the origin. Okay. So, spherical coordinate system Okay. One of the coordinates is the distance from the origin. Okay. So, if I define the distance from the origin to a point as r, then the surface is just given by r is equal to capital R. Okay. So, the surface of the sphere is a surface of constant coordinate. Therefore, it makes sense to solve this in a spherical coordinate system. Okay. So, I will go through the spherical coordinate system in some detail in order to make the physical interpretation clear. Okay. So, I will draw it a little bigger for you. Okay. In a spherical coordinate system, this is the Cartesian coordinate x, y and z. Okay. In a spherical coordinate system, if you have some position here, okay, some position here, it is usually defined as x vector, which you can express as x Ex plus y Ey plus z Ez. Okay. In the spherical coordinate system, as I said, one of the coordinates is the distance from the origin. Okay. That is called r in the spherical coordinate system. The distance of that point, any point in space from the origin. The second coordinate, okay, so radial coordinate is r. Okay. The second coordinate is the angle made by the position vector with the z axis. Okay. This is what is called the azimuthal angle. Theta. Okay, the angle made by this position vector with the z axis is the azimuthal angle theta. The third one is you take the projection of this position vector onto the xy plane. Okay. You take the projection of this position vector onto the xy plane. The angle made by this projection with the x axis is what is called the meridional angle. So, since this angle, the azimuthal angle is theta, the height above the x plane above the xy plane is r cos theta, and this distance from the origin to the projection is r sin theta. Okay. And the total distance is r. Okay. So, based upon that, you can easily see that the z coordinate is just equal to r cos theta. Okay. The x coordinate is equal to this distance from the origin times the cosine of this angle phi. So, this is r sin theta cos phi, and the y coordinate is basically the same distance times sin phi. Okay. Because if this is phi, then this distance will be equal to pi by 2 minus phi. So, y will be equal to r sin theta sin phi. In the reverse direction, r is equal to square root of x square plus y square plus z square. Okay. Theta you can get from by taking square root of x square plus y square. Square root of x square plus y square is r square sin square theta cos square phi plus r square sin square theta sin square phi, just becomes r square sin square theta, okay, divided by z. Okay, the square root of that is r sin theta divided by z. This is equal to tan theta. Okay, and you can easily verify that tan phi is equal to y by x. So, these are the conversions between the spherical and the Cartesian coordinate system. To give you some better physical insight into the spherical coordinate system, I will relate it to a coordinate system that many of you should be familiar with, that is the latitudes and longitudes on the Earth's surface. Okay. So, if you recall, on the Earth's surface, okay, these are the two poles. This is the north pole, this is the south pole, and this is the equator. Okay. Equator is usually defined as, okay, theta is equal to pi by 2. Okay. And I will relate this to what I had here, okay, in the spherical coordinate system. Okay. Equator is usually given latitude 0 degrees. Okay. Equator is usually given latitude 0 degrees. The north pole is given latitude plus 90 degrees and the south pole is given latitude minus 90 degrees. Okay. And then you have the tropics, okay, and the Arctic and the Antarctic circles. Okay. So, these are at okay, 33 degrees and 66, okay, and so on the rear side, minus 33. Okay. So, this equator 0 degrees corresponds to theta is equal to pi by 2. Okay. Okay. Because this angle theta is pi by 2 along the equator. Okay. In this, if we take the xy plane along the equator, and this the axis from the north to the south pole as the z direction, and the xy plane in the along the equator, then theta is equal to pi by 2 is equivalent to the equator. North pole is theta is equal to 0, okay, because the angle theta is 0 at the north pole. The south pole is theta is equal to pi. Okay. So, in our azimuthal coordinate system, theta is equal to 0 corresponds to plus 90 degrees for the latitude, theta is equal to pi corresponds to minus 90 degrees for the latitude, and theta is equal to pi by 2 corresponds to 0 degrees. Okay. So, that is the equivalence between the latitudes on the Earth's coordinate system and the azimuthal angle for the spherical coordinate system that we will use. Okay. It is almost exactly the same, except that the convention is slightly different. What we consider 0 degrees for the azimuthal coordinate system is plus 90 in the geodesic coordinate system. South pole theta is equal to pi for us is minus 90, and the equator is theta is equal to pi by 2, which is 0 degrees. The meridians are exactly the same as the phi coordinates. Okay. The meridians that go around the circle, okay, they are exactly the same as the meridional angle. Basically, you take a projection here and take the phi direction here. Okay. So, the phi meridians on the Earth's surface is identical to the meridional coordinate system for our spherical coordinate system, whereas the azimuthal angle is directly related to the latitude. Theta is equal to 0 corresponds to plus 90 degrees centigrade, plus 90 degrees, theta equals pi corresponds to minus 90 degrees. Okay. So, minus 90 degrees is minus pi by 2. So, when theta is equal to pi, the latitude is minus pi by 2, theta is equal to 0, the latitude is plus pi by 2, theta equals pi by 2 is the equator. Okay. So, that is the equivalence between the spherical coordinate system that we will use and this coordinate system on the Earth's surface, the latitude and the longitude on the Earth's surface. Okay. So, now in the spherical coordinate system we have to do derive the mass conservation equation. Okay. So, if you recall, when we did the mass conservation for the Cartesian coordinate system, we took two surfaces perpendicular to the x axis, two surfaces perpendicular to the y axis, and two surfaces perpendicular to the z axis. Okay. And the unit vectors there were Ex, Ey and Ez. In this coordinate system, the unit vectors are different. Okay. The unit vector Er unit vector ER is along the direction of variation of r, okay, because as you vary r, as you vary the distance from the surface, the radial coordinate varies. So, therefore, the variation of the radial coordinate is along the direction of the unit vector in that direction. The theta coordinate is in this direction, okay, theta is increasing in this direction. Therefore, E theta has to be in this direction. Okay. And E phi is increasing in this direction. E phi is increasing in this direction. That means that the unit vector in the phi direction is in this direction perpendicular to the plane. Okay. And at each position in space, each of these three is perpendicular to each other. The ER, E phi, E theta and E phi are each perpendicular to each other at each position in space. Okay. However, it is easy to see that ER, E theta and E phi do vary with spatial position. Okay. So, if I took some other location here, okay, if I took some other location here, the unit vector ER would be in this direction. Okay. And these two are not in the same direction. Okay. In contrast, if you recall in the Cartesian coordinate system, Ex was in the same direction at all points in space. In this coordinate system, ER is not in the same direction at all points in space. So, the unit vectors do depend upon position, but at each location each unit vector is perpendicular to the other two unit vectors. So, they form an orthogonal coordinate system. And in this, it is in this coordinate system that we will be deriving the conservation equations. Okay. So, if you recall, in the Cartesian coordinate system we had considered 6 surfaces, 2 each were perpendicular to the ER direction, to the x direction, 2 were perpendicular to the y direction and 2 were perpendicular to the z direction. Okay. So, in this case as well we have to consider 6 surfaces. 2 of these surfaces are perpendicular to the r direction, 2 of these surfaces are perpendicular to the theta direction and 2 of these surfaces are perpendicular to the z direction. So, this is r, this is theta and this is phi. Okay. 2 surfaces are perpendicular to the r direction. Okay. So, these 2 surfaces that are perpendicular to the r direction are surfaces of constant r. Okay. Okay. So, this surface is at r plus delta r by 2, this surface is at r minus delta r by 2. Okay. So, we have 2 surfaces that are perpendicular to the r direction. Okay. Okay. 2 surfaces perpendicular to the theta direction and 2 surfaces perpendicular to the phi direction. Okay. And we have to determine what is the surface area of each of these. Okay. So, for that we first have to determine what is the surface area of an elementary arc in each of these directions. Okay. So, let us go through that first. This is the radial coordinate. If I change the radial coordinate by a small distance delta r, okay, if I change the radial coordinate by a small increment delta r, the distance travelled in r direction is equal to delta r itself. Okay, if I go a small, if I change r by a small amount delta r, the distance travelled is delta r itself. Now, if I change theta by a small amount delta theta, okay, so if I go from theta to, okay, a small increment delta theta in the theta direction, what is the actual distance travelled? It is not delta theta, because theta is an angle, it has no dimension. The actual distance travelled is the length of this arc over here. Okay, so, the distance in theta direction is equal to r delta theta. Similarly, if I increase the angle phi by a small amount, okay, by a small amount delta phi, what is the actual distance travelled? Okay, distance in phi direction. Okay, note that this distance from the center, okay, this distance from the center is equal to r sin theta. Okay. And therefore, this arc, the distance travelled when phi changes by a small amount delta phi, is going to be equal to r sin theta delta phi. Okay. So, these are the fundamental dimensions that will be used for defining our differential volume. Okay. So, let me construct the differential volume for you. This is r, this is theta, and this is phi. Okay. So, the surfaces bounding this differential volume in the r direction are at r plus delta r by 2 and r minus delta r by 2. Okay. Radius is constant on these two surfaces. I will draw it big over here. Okay. Okay. At r plus delta r by 2, you are varying theta. Okay. Theta varies over delta theta, that means that the distance travelled is r delta theta. Okay. And the phi is varying in the phi direction by delta phi in the phi direction. Okay. That means that this distance is r sin theta delta phi. Okay. So, this is the surface at r plus delta r. Okay. There is a surface at r plus delta r, and strictly speaking this should be r plus delta r into delta theta, and this should be r plus delta r sin theta delta phi. This is the surface at r plus delta r. Okay. And the surface at r also has two perpendicular displacements, that is r sin theta, r delta theta, and r sin theta delta phi, which will be this distance. Okay. This distance here is going to be equal to r sin theta delta phi. Okay. So, these are the two bounding surfaces in perpendicular to the r direction. Okay. Then you will have two bounding surfaces perpendicular to the theta direction. Note that the direction of variation of theta is this one. Okay. This is the direction of variation of theta. Okay. Therefore, I have two surfaces here perpendicular to the theta direction, okay, at theta and theta plus delta theta. Okay. And the surface area of these two surfaces is displacement in the r direction is delta r, displacement in the r direction is delta r, and the displacement in the phi direction is r sin theta delta phi. Okay. And then I have two surfaces perpendicular to the phi direction, and those will be these two surfaces here and this one. Okay. And the surface perpendicular phi direction has increments in the r and theta direction. Increment in the r direction is delta r, and in the theta direction is r delta theta. Okay. So, it is for these 6 surfaces, and the volume, which is the increment in the r direction, theta direction, and phi direction. It is for this differential volume that we will be writing the conservation equation for. I will review this again in the next lecture and proceed to derive the conservation equation. This, as I said, is chapter 7.2 in the textbook. Kindly go and review it, and I will continue this in the next class. We will see you then.